Good afternoon, all.
Good afternoon, sir.
Um, okay, we'll continue the lesson. ఒక్క సెకండ్ కొంచెం రెవెన్యూ సిస్టమ్ Okay, yesterday we have stopped at the just we are introducing about the what are conjugated ions. Where we have seen the different examples of conjugated 1,3-butadiene and how it is in the isomeric forms and 1,3,5-hexatrienes and 1,3,5,7 octatrienes. Okay. Now, whenever these conjugated ions are subjected to photochemical reactions. What is happening in the previous case? These olefins or alkenes, or either it may be conjugated alkenes, conjugated double bonds, or unsaturated systems. They are undergoing cis-trans isomerization reactions and some acyclic addition reactions that takes place on alkenes. But in the case of these conjugated ions, the reactivity is different. The reactivity is different due to the negligible intersystem cross efficiency. That means triplet energy transfer. Actually, 1,3-butadiene or 1,3,5-hexatetraenes, it is these are having the triplet energy states are somewhat higher energy. Therefore, whenever we are directing irradiation of this compound or direct irradiation of these conjugated dienes, involves to produce 5 to 5 star singlet states. Suppose if the reaction is involving any sensitizer, there is no need to absorb the radiation by the conjugated system. That sensitizer can absorb the radiation, then that will be transferred to the conjugated ion systems or conjugated systems. Then it will directly lead to the formation of 5 to 5 star triplet states. That is called triplet sensitization. When the sensitizer is available, uh, just conjugated ion will not absorb any radiation, or if it is absorbed radiation, it will not get excited to corresponding excited state. That corresponding triplet energy state will be found by the sensitizer only. So, if we consider the first example of conjugated ions is 1,3-butadiene or buta 1,3 diene. It is the typical member of this group. This is the first group and also important compound. This is in the solution state. Suppose this compound is mixed in a particular solution, or if it is in the solution state, it is rapidly gets isomerized to produce the equilibrium mixture of the S cis and S trans will be generated. Yesterday we seen that this is the 1,3-butadiene. This 1,3-butadiene gets this 1,3-butadiene easily undergoes the isomerization at normal conditions, even though in the absence of light also they are easily undergoing isomerization in the solution state. Therefore, they are rapidly undergoes isomerization. It produces S cis of 1,3-butadiene and S trans of 1,3-butadiene. At normal conditions, it will be the ratio is cis is 1% and trans is 20%. That is 1 is to 20 ratio of this of the portions proportions is observed. Proportions is observed. Is observed. Okay. Now irradiation of the solution of butadiene gives a mixture of products. Suppose this mixture is, well, again I am drawing this. This is S 13 butadiene and you consider S trans 13 butadiene. Both will be irradiated when it is in the solution form. Solution form, right? That is an irradiation. It gives a mixture of products. What are that mixture? That is cyclobutene, cyclobutene, you know that the cyclobutene is like this. First I read the structure, later I write it. Cyclobutene, that is simply they are undergoing electrocyclization. This product is responsible by the electrocyclization. In the pericyclic reaction, we studied about the electrocyclization. Electrocyclization. Electrocyclization is responsible for the formation of one cyclobutene originally. Simply I'm calling it as cyclobutene. And the second compound is bicyclobutene. The bicyclobutene is like this. This is the bicyclobutene. Along with the mixture of cyclobutene derivative this is one isomer this is next isomer and this this named as these two compounds are named as yeah, both I'm combined together and I'm writing here. Cis trans, cis and trans, 1,2 divinyl cyclobutane, divinyl cyclobutane. Along with these four products, another product is this is called 2-vinyl bicyclo 3,310 hexane. It is the one product, right? Next, cyclooctadiene derivative. Cyclooctadiene derivative. This is cyclo 1,5 1,5 A octadiene. These are the almost 6 products are generated. The 6 products are generated in which the first two are these two, 1 and 2. These are the major products. 1 and 2 are the major products. The remaining 3, 4, 5, and 6. These are the products 3, 4, 5, 6 are dimerization products. Dimerization products. These dimerization products are the minor products. Minor products. The yields are less than total, all 4 products are less than 10%. These two are the 90% products, both combined together. And the last 4 are both combined to produce only 10% of the products. 10% of the products. Right. Before understanding the mechanism, already we know that in the solution of buta 1,3-diene or 1,3-butadiene exists as a rapid isomer equilibrium mixture, that is S cis and S trans in the ratio of 1:20. That is, the proportion is 1 molecule of S cis and 20 molecules of S trans observed in the solution. Right. Then absorption of radiation by the conformer gives corresponding singlet excited state. Singlet excited state without changing any nuclear positions. Without changing any nuclear positions. How it is generated? First, you take both the isomers. This is the S-cis isomer. Now, these two are in equilibrium. That means one molecule is S-cis conformer and 20 molecules of S-trans conformer. This is the ratio at equilibrium. Now, both is the mixture. Both will be subjected to photochemical irradiation at that particular required wavelength. Then they both gives the transition state. The transition state is 1,4 biradical. 1,4 biradical. This is the transition state. 1,4 singlet biradical. Here is also. It generates one comma 4. 1, 2, 3, 4. 1 comma 4 singlet biradical. Now, the singlet biradicals is undergoes electrocyclization. Electrocyclization that leads to the formation of cyclobutene, which is undergoing cross addition reaction. Cross addition reaction. What is the cross addition? If you take this is the 1,4 biradical. Now this is also a double bond. The double bond during the reaction exists in this form. Right. Now these two electrons are combined together to form the one bond at the transition state. These two electrons are combined together to form the bond. That means the electron containing orbitals or molecular orbitals are overlapping each other. That means 1, 2 position molecular orbitals are combined together which contains the single electron. They can produce the pi bond. Here also single. Then, sorry, just. That means previously that is the reversible. Suppose the condition is not reversible condition. In such case, what's happened? This is a 1,4 biradical, and the 1,4 biradical. These two electrons are combined together, they produce the bond, sigma bond. These two electrons are combined together, they produce the bond. Now that leads to the formation of this is called bicyclobutane. Called bicyclobutane. Okay. What type of reaction it is? It is believed that S-cis conformer or S-cis conformer is the precursor for producing the cyclobutene. That only cis product can generate the cis product can only generate the cyclobutane product. Similarly, the bicyclobutane can be obtained from the S-trans conformation. In your book, it will be S6 and Padari. You make it change. That is responsible by the S-trans. This product formation is responsible by the S-cis. This product is responsible for the formation of cyclobutane. This product formation is responsible by the S-trans precursor. Right? Therefore, the first two products are explained. The formation of these two products are explained. Formation of two products are explained. That mechanism is also explained. Now, how the remaining products are generated. How the remaining products are generated can be explained. Look at here. In these two cases, it is not required any triplet sensitizer. Directly it produces singlet state. That singlet state in both the cases, 1,4 biradical singlet state is involved in the reaction that creates the formation of these two products. These two products are major products in the above reaction. Right? Uh, in view of the support of the reaction, cyclic dienes, suppose the formation of these products can be proved by how it is proved. Here we are taking the 1,3-butadiene, cis or S-trans starting materials are highly flexible. How it is flexible? The CC single bond is undergoing rotation whenever we are irradiation with the light. Suppose we are irradiating the compound with light, both the compounds undergoing CC rotation. CC bond rotation. Therefore, we cannot predict only the cis product gives the cyclobutene, only trans product gives the bicyclo product, cannot be predicted. That can be confirmed by a rigid cyclo, rigid conjugated diene systems. Instead of this S-cis trans starting material, instead of this S-cis trans, S-cis product or S-trans product. For this replacement, I am considering just octa heptadiene, 1,3-butadiene resemblance structure, but it is cyclic and just 7-membered. This is the 7-member ring. Look at here. Just the rotation of the CC bond is restricted by making this into form of cyclic systems. Here also, instead of the trans S trans isomer, I just considering the a fused ring system in the trans manner. This will be considered. What's happening when these two are considering completely? The same reaction is carried out whenever we are applied the irradiation wavelength for the above reaction. At the same wavelength, the reaction is conducted. The reaction is conducted. Whenever we are irradiated with light, it generates the direct irradiation. No sensitizer is required there. On direct irradiation, it will be prohibiting the CC bond rotation. There is no CC bond rotation is observed here. No CC bond rotation. Then it leads to the only can generate the cyclobutane derivative. Only it can generate the cyclobutane derivative. Cyclobutane derivative. That is a fused ring system is generated. That means when you are considering up to this, it generates the only cyclobutane fused ring system. Now we are here. This is the isomer is S cis isomer. When you consider the S trans isomer, by using these systems, actually what compound is actually responsible? What compound is actually responsible for the formation of cyclobutene and bicyclobutene? Now this compound irradiated with the light and direct irradiation. Here there is no CC bond rotation. No CC bond rotation. Then that leads to the formation of this kind of product. Okay, look at here. Up to this is the bicyclobutane derivative. It is fused with the other 5-member rings. Bicyclobutane. Now look at here. Up to this one, how it is resembles like that? Yes, trans butadiene. It is resembles with the one S trans butadiene. Thus, trans can only produce bicyclobutane. Cis isomer can only produce cyclobutane. Can be are revealed by these two examples. Are revealed by these two examples. Now, when you come into the triplet state energies of the 1,3-butadiene are quite different. In photochemical reactions of 1,3-butadiene, in presence of a triplet sensitizer, dimers are found in more than 75 yields than the whatever the products we predicted, that is cyclobutane butane derivative and bicyclobutane derivatives. Okay. Whenever the 1,3-butadiene is direct irradiation, the major products are cyclobutene and bicyclobutane is the products, are the major products. Only 10% is that dimerization products are generated. Instead of the same reaction is conducted in presence of a photosensitizer that leads to the increasing the percentage of dimerization products at the same time decreasing the yields of cyclobutane and bicyclobutane products, right? But it is also depends on the sensitizer which is used in the reaction. It is also depends on the sensitizer used in the products, right? Here we are going to understand the how dimerizations are takes place. If you are taking, you take any isomer that will be generate the equilibrium mixture. You take a cis product or S trans product that means that may undergoing the equilibrium isomerization and reaches the equilibrium. Both the products will be generated, which is irradiated in presence of triplet sensitizer. Triplet sensitizer. It gives three kinds of products, major products I am going to discuss here. Three kinds of products. One is cis 2-vinyl cyclobutene and trans 1,2 divinyl cyclobutane. Both are isomers, structural isomers. Cyclobutane, sorry, geometrical isomers. Next, the fourth one is these two products are due to the 2+2 cycloadditions. Cycloadditions. Then when you come to the next last product, in the presence of triplet sensitizer, these kind of products are appear. There is 4-vinyl cyclohexene. 4-vinyl cyclohexene is the product. These three products mixture is generated when the 1,3-butadiene is irradiated with light in presence of triplet sensitizer. Right. The dimerization composition is always depends on the triplet energy of the sensitizer. In any triplet energy sensitizer, which is having the highest energy triplet sensitizer, the product ratio is almost same. The same ratio of dimers and the product which is obtained in the 4+2 cycloaddition reaction. 4+2 cycloaddition. This is responsible for 4+2 cycloaddition. These two are the responsible for the 2+2 cycloaddition. Right. Now, the dimer composition, all the products are dimers. This dimer composition is always depends on the energy of the triplet sensitizer. If the triplet sensitizer is the higher energy triplet energy sensitizer, the product ratio will not change. The ratio will not change. But when the sensitizer energy, triplet state energy is falls less than 60 kilojoules, sorry, kilocalories, less than 60 kilocalories, but above 53 kilocalories per mole, the percentage of this product, the percentage of 4-vinyl cyclohexene, 4-vinyl cyclohexene product yield will be increases by the expensing of this divinyl cyclobutane product. This whatever the cis trans products are there, these will be consumed. Then the product of the 4-vinyl cyclohexene amount will be increasing gradually in this energy region. In this energy region, for knowing the clear difference at the different triplet energy sensitizers. Suppose I am going to take different sensitizers. What are the ratios of the product? sensitizer, and triplet energy state in the kilocalories per mole, dimer composition, in percentages. Next to in which the first 2 plus 2 cyclic products, that is 1,2 divinyl cyclobutane, that is a cis isomer and a trans isomer. And the last one is these two are responsible for the 2 plus 2 cyclic, and 4-vinyl cyclohexene, how these products rates will be changed when sensitizer is changed. For example, I am taking estophenone. The estophenone is the sensitizer, triplet energy sensitizer. The triplet energy is the range 73.6 kilocalories per mole, and the yield of the cis isomer of the 2 plus 2 addition product is 19%, and the trans product yield is the 78%, and this 4-vinyl cyclohexene ratio is the 3%. Similarly, if you are using benzaldehyde as a triplet energy sensitizer, a triplet sensitizer, simple sensitizer, the ratio of the energy of the triplet energy is, it can able to transfer 71.9 kilocalories per mole. But slightly the cis isomer yield will be decreases. Slightly the cis isomer yield is decreases, but slightly trans isomer yield is increases. At the same time, 1% of 4-vinyl cyclohexane product is increases. But no need to by heart it, but whatever the concept we need to understand here. Next, if you are using benzophenone is the triplet energy sensitizer, it can able to transfer 68.5 kilocalories per mole, and slightly increasing the cis isomer. And when you compare the second one, but when you compare the first one, it is the lower value, decreasing that yield, and the same yield of trans product. But when you coming to 4-vinyl cyclohexene, here also the yield is decreases. Yield is decreases only 2%. Now this is the borderline. This is the optimum level to get the 1,2 divinyl cyclobutane. This is the optimum radiation and optimum sensitizer to get the maximum yield of the trans product and 1,2 divinyl product. Only 2% of that 4-vinyl product is generated. But when you going down to the borderline, what's happening? If we are using beta naphthaldehyde, this is the naphthalene. This is the beta naphthaldehyde. The energy can able to transfer is 59.5 kilocalories per mole. The cis isomer can be 17%. The rapidly the trans isomer amount is decreases from 80 to 71. Then that from the 2 to 12% it is increasing the 4-vinyl cyclohexene product. Similarly, if you are using alpha naphthaldehyde, this is the alpha naphthaldehyde. This can be transfer 56.5, 56.3, 56.3 kilocalories per mole. Again, it continues to decreasing the yield of cis isomer and also the trans isomer, but raising the yield of 4-vinyl cyclohexene. And diacetone is the sensitizer. It leads to the can transfer the 54.9 kilocalories and it is responsible for the 13% of the cis isomer, 52% of the trans isomer, 35% of the 4-vinyl cyclohexene percent. Bibenzones is the photosensitizer. Again, it rises and decreases to 53.7. Sorry, it can able to transfer 53.7 kilocalories of energy. Now drastically downs to 10% and a 44% of trans isomer, and it leads to the 45%. Now this table clearly indicate that when we are maintaining the triplet sensitization in between the 56 below the 60 and above the 53, we will get the more amount of 4-vinyl cyclohexane, but at the same time the yields of the cis and trans divinyl cyclobutane is decreasing. The results can be explained by the energy of triplet state of S and trans conformer and the barrier to rotation about the C1C3 bond in the highest occupied molecular orbitals of that is HOMO of the diene in the excited state. In the excited state, we are saying that it will be in the triplet state. In the triplet state means it will be in the first excited state of the triplet state. First excited state of triplet state. Right. In the Jablan skill diagram, clearly you can explain that what is the first excited state of triplet state and what is the second excited state of triplet state. At the same time, first excited state of single state, first excited state, second excited state of single state. Everything is explained. Here we are considering first triplet energy state. In the triplet energy state, how it is like that. First, you need to understand the molecular orbitals of 1, 3. I think how many of you are read the pericyclic reaction? I don't know. The molecular orbitals of 1,3-butadiene is already explained. Look at here. This is the 1,3-butadiene. Whether you take this S6, either this one, this is the S6. Either it is S trans. Sorry. Right. Now, all the carbons, 4 carbons are there. All 4 carbons are having one hybridized atomic orbitals. These are undergoing linear combination LCAO that leads to produce the 4 atomic orbitals are 4 atomic orbitals are combined together. That leads to formation of linear combination of atomic orbital. That leads to formation of 4 molecular orbitals. 4 molecular orbitals. In the 4 molecular orbital, 4 by 2 are the that is the 2 bonding molecular orbitals. 4 by 2 are the 2 anti-bonding molecular orbitals. Now this is the non-bonding energy level. Non-bonding energy level. We have 4 molecular orbitals are generated. right? In the four molecular orbitals, the least energy orbital is like this. You can represent like this. These are the two bonding molecular orbitals. Just a bit. Okay. These are the first two. It is indicated with this psi1, psi2. These two are the bonding molecular orbitals, lower energy orbitals, and psi3, psi4 is the pi molecular orbitals. These are the designations, and the number of nodes, that is n minus 1 nodes. The number of nodes are equal to n minus 1. Suppose here the psi n, where n is equal to n minus 1, that gives the number of nodes. 1 minus 1, 0 nodes. That means there is no node at any point of that molecular orbital. Here it is 2 minus 1, 1 node. The node is here. And 3 minus 2, 3 minus 1, 2 nodes. One node is here, and another node is here. Right? So 4, that means 3 nodes are there. The node points are here. These are the 3 nodes. Now, whenever we are coming to the energy levels, we need to understand the what is the ground state electronic configuration. Each atomic orbital is having one electron. Each atomic orbital is having one electron. That means 4 electrons are there. How these 4 electrons are filled in the molecular orbital? Suppose this is the psi1 and psi2, psi3, psi4. At the ground state, this is the non-bonding energy level. The 4 electrons are there. It follows the Apo principle and Pauli's principle and Hund's rule. Then the lower energy orbitals are first filled. And then this is the ground state electronic configuration. Ground state electronic configuration of 1,3-butadiene is psi1 2, psi2 2, psi3 0, psi4 0. Whenever we are subjected to when we are subjected to irradiation with the light, irradiation with the light, the electron is excited from the psi1 to psi2 to reach the first excited state, whether it is maybe a singlet excited or a triplet excited. Suppose that is reached to a singlet and triplet energy in the presence of celestial. This is the electronic configuration of the first excited state. It is psi1 2, psi2 1, psi3 1, psi4 0. Now, in the ground state electronic configuration, highest occupied molecular orbital. What is HOMO? HOMO is highest occupied molecular orbital. The orbital will be filled with which is having the highest energy. That is called HOMO. Now here psi1, psi2, psi3, psi4. Which one is filled? Psi1 and psi2 are filled. In which one is having higher energy? The psi2. Therefore, this is known as HOMO. That is the ground state HOMO of the 1,3-butadiene is psi2. And next one is LUMO. What is LUMO? Lowest unoccupied molecular orbital. That means lowest means lowest energy unoccupied molecular orbital. Here psi3, psi4 are empty. Therefore, which one is having lowest energy? Psi3. Therefore, this is the LUMO. This is the HOMO, this is the LUMO. When which is an irradiation, this electron is excited from this HOMO to LUMO. At the ground state, HOMO is psi2, LUMO is psi3. After irradiation, it reaches to first excited state. What is the first excited state HOMO? Occupied highest energy molecular orbital. This is the HOMO. What is LUMO? That is the empty orbital which is need to be have the lowest energy. That is LUMO. These HOMO LUMO molecular orbitals geometry is influences the formation of that above dimerization products ratio in presence of photosensitization. Right? What's happening in the first excited state of 1,3-butadiene? The psi3 is the LUMO, psi3 is the HOMO. In psi3, there is greater barrier. Greater barrier means that it requires higher energy to rotation about the C2 C3 bond. Look at here. For undergoing isomerization, it needs to, in this case, for undergoing isomerization, either in the cis isomer or trans isomer, this sigma bond should be undergoing rotation. This sigma bond going to be undergoing rotation. Therefore, for the barrier, whatever the energy required for this that CC bond rotation called as energy barrier, that energy barrier is the greater energy barrier. That means highest energy barrier to rotate about the C2 C3 bond of the triplet state of S cis and S trans conformation of butadiene. Right. But when the sensitizer, whatever the triplet sensitizer is used in the reaction, that facilitates that. When energy of triplet state of sensitizer is more than 60 kilocalories per mole, right? Suppose if you are using sensitizer like benzophenone or other anything, benzaldehyde or acetophenone, whatever it may be, when that the energy of the triplet state of sensitizer is more than 60 kilocalories per mole, the triplet energy is transferred to the first diene molecule it encountered, that is S-trans conformer. S-trans conformer nor the S-cis conformer. That means if the sensitization energy is more than 60 kilocalories per mole, S-trans isomer can only bombarding with that sensitizer that will be converting into corresponding triplet state. This is in turn attacks another butyl. That is whatever the S-trans conformer which is reached to the triplet state that will be bombarded with the another isomer of butadiene molecule in the ground state, which again whatever the another butadiene is, that is also S trans conformer, that results the triplet 1,4 biradical is a resonance hybrid of several structures. It can cyclize to whatever after formation of 1, 4 biradical. That 1, 4 biradical again is reacting with the same S trans isomer of the butadiene that leads to the formation of or it leads to the cyclization to produce cis and trans 1, 2 divinyl cyclobutene, but not the 4-vinyl cyclohexene. Due to the large barrier to rotation about the original C2C3 bond of the S trans isomer is mainly responsible for the formation of S cis and cis trans 1, 2 divinyl cyclobutane products. But however, a small amount of 4-vinyl cyclohexene is results by the reaction of T1 state of S trans conformer with a S cis conformer in the ground state, which is present in the small portion in the reaction vessel. Whatever the 1,4 biradical transition state of S trans isomer is reacting with cis S cis isomer that leads to the formation of 4-vinyl cyclohexene product. How it is generated, I will show the mechanism here. First, I am starting with the S trans isomer. Here I am going to take the S trans. It will be radiated. It is not direct irradiation. Irradiation of the compound or of the starting material in presence of sensitizer. The energy of the triplet state, that is also first triplet energy state, is greater than 60 kilojoules, 60 kilocalories per mole. The sensitizer can provide the triplet energy transfer. It is involving above 60 kilocalories per mole. Then directly treats a triplet 1,4 biradicals. Triplet 1,4 biradical. This 1,4 biradical directly reacting with a ground state of S trans, isomer. This is in the S naught state, ground state. Then it occurs the two-way attacking on the ground state S trans product that leads to the formation of two transition state or two intermediates. This is also triplet excited state one. This is the product, one of them. And next one, actually when you numbering 1, 2, 3, 4, 5, 6, 7, 8. 1, 8 biradicals. Both are 1, 8 biradicals. 1, 8 biradical intermediates. Now, these are again rearranged. These are undergoing rearranging. That means this double bond is undergoing homolytic cleavage. Now, whatever the electron here there in the double bond is combined with this electron pair together that produces form pi bond. Now it creates the radical here. Then but these two positions will not combine together. That will not lead to any. It will not lead to any of this cyclohexene derivative. 4-vinyl cyclohexene derivative is not generated from this intermediate. Okay, this intermediate this can be generates only then both will be combined. Again, this pi bond is also undergoing homolytic cleavage. Now these two will be undergoing a bond formation that leads to the right. This is the product, subproduct is obtained. This is the trans product here. Trans 2 comma 1 comma 2 divinyl cyclobutane is the one product. Now, the second transition state, whatever the 1 comma 8 by radical, second transition state, here also the same mechanism. It undergoes the 5 bond cleavage, homolytic cleavage, that form the rearranging of double bond. Here also that produces this. Again, this bond is undergoing homolytic cleavage. There is a 2 electrons are there here. These 2 electrons combine together. Then it produces the sigma bond. That is the product. This is called cis 1 comma 2 divinyl cyclobutane. Divinyl cyclobutane. Then, but get here. Whenever we are
Sir,
calculating,
cis అని ఎలా చెప్పారు?
yes, yes.
Sir, cis అని ఎలా
When
చెప్పారు?
you imagine that, suppose here in case cis trans can be explained like this. Suppose here I am going to take, right? Simply, you can easily observe that the above bond is, this bond will be above the plane, right? This will be above the plane, right? This bond will be below the plane. This bond will be above the plane. This bond will be below the plane, right? Did you understand? Right. These two are the same side. Therefore, these two are cis bonds. These two are the same side. A and A, same side. B and B, same side. A and B, sorry, A and A and B and B are cis, the bonding nature. Right. A and B and A are the trans. Did you get my point?
Okay.
Okay.
Yes, sir.
Now here, when you look into here, these two are the above the bonds, above the plane of the bond. Suppose the plane is a 4-member ring is within the plane. These two bonds are above the plane. Both are on the same side. Look at here, the A and A bonds. A and A bonds. Both are cis. Previous one. Look at here. This bond is the A type bond. This one is the B type bond. Both are in opposite faces of the plane. A is the above the plane, B is the below the plane. Both are opposite to each other. Now that becomes
Trans.
plane. Sorry,
Trans.
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 Yes, yes. Therefore, this is the cis trans isomers are generated in this way. These two isomers can be only generated by the S trans, this S trans 1 comma 3 butadiene. Once this S trans butadiene is irradiated with light in presence of sensitizer, that energy of the triplet state energy transfer is above 60 kilocalories. It generates the 1,4 biradical, 1,4 biradical triplet state, triplet state that will be bombarding with the ground state S trans isomer. Then it leads to the formation of trans 1,2 divinyl cyclobutane, cis 1 comma 2 divinyl cyclobutane. Right. Then other remaining product. What is the product remaining? The 4 vinyl. Right. Why here this 1 comma 4 biradical is trans method? This only this trans can I'm here shown. That is the only triplet energy state of the transition state is generated in this reaction. Why? Already we know that when the 1,3-butadiene diene is taken in a vessel at the room temperature, that will be exist in the form of 1:20 ratio. The 1% is the cis form, 20% is the trans form. Therefore, whenever we are irradiating with light in presence of sensitizer, the more population is the 1,4 biradical transition state is the trans state. Then this will be again instead of the ground state of S trans conformer, it will be reacting with S cis conformer. A ground state of S cis conformer. It will give the intermediate transition state. The transition state becomes again 1 comma 8 biradical, 1 comma 8 biradical. That 1 comma 8 biradical will be like this. How it is generated, I will show you. Right, this one. How it is generated, I will show you here below. Now, this is the S cis conformer and S trans conformer. This is the triplet excited state. Triplet energy excited state. This is the ground state, which is bombarding with that one. Now this bond will be homolytically cleaved. That leads to the here one electron is unpaired. Now this will be bonded here. This carbon is bonded to here. Then this is the carbon is this one, right? Here the double bond is there. This is called 1, 2, 3, 4, 5, 6, 7, 8. This is 1 comma 6 biradical 2 comma 7 diene diene dioptene and simply dioptene. Octave otherwise octadiene. That is the biradical system is generated. This is the way that this will be generated. Look at here. 1, 2, 3, 4, 5, 6. Here the bond is there. Right. Now, what's happening next? This will be produces the cyclohexane derivative. Is next undergoes the cleavage of this bond, the cleavage of this bond, then it leads to the formation of this bond. Here one electron is left, and again this bond is undergoing the homolytic cleavage. Here one electron and here an electron. And you can show in that it is still. Both will homolytically combine. That leads to formation of. Here I am showing half of Keras. Whenever the bond is involving in the homolytic cleavage or homolytic formation, we need to show in the half of Keras. That is the product. Then 1, 2, 3 vectors. Distances. 1, 2, 3, 4. This is the 4-vinyl cyclohexene. That is the product. Okay. Then it is clearly pictured how the 1, 2 divinyl cyclobutane is generated and 4-vinyl cyclohexane is generated. 4-vinyl cyclohexane is only generated from the cis trans, S cis trans 1, 4 biradical transition state is combined with the undergoing the dimerization with the S cis conformer that leads to the formation of 4-vinyl cyclohexane. But 1, 4 S trans biradical transition state is reacting with ground state of one S trans conformer that leads to the formation of a mixture of cis and trans 1, 2 divinyl cyclobutene derivative. Right? This is the mechanism. It is clearly explained. In both the cases here, you can understand that when the trans-trans isomer both together combining is involving 2 plus 2 cyclohexane, and when the trans biradical system and cis conformer is undergoing the 4 plus 2 cyclohexane reaction. That you need to remember. And last important example 1, 4 diene rearrangement reaction, that is also called diphenyl-methane rearrangement. Without this question, exam paper will not appear. Right? Without appearing this question, there is no exam paper will come. Right? This is that much important. That is diphenyl-methane rearrangement. Call it as diphenyl. Diphenyl-methane rearrangement. This is also called photochemical rearrangement of 1, 4 biradical. Sorry, but 1, 4 dienes. 1, 4 dienes. How it is undergoing 1, 4 dienes. In this reaction, 1, 4 dienes, these are the isolated dienes. These isolated dienes undergoing the photochemical cyclization that leads to the formation of vinyl cyclopropane derivatives. Vinyl cyclopropane derivatives. How it is generated, I will show the one example. Then you can practice several examples from your book. Okay, this is the isolated diene of 1,4 pentadiene. This 1,4 pentadiene is irradiated with light. Direct irradiation, no need of sensitization. Here there is no need of sensitization. That leads to the formation of a vinyl cyclopropane is generated, or is also represented similarly. You can also represent like this. That is the product. Vinyl cyclopropane is the product. Then what is the mechanism involved? Coming to the mechanism, just I explain the mechanism and close the session. Mechanism. You take that 1,4 pentadiene system, right? Whenever we are irradiating with light and direct irradiation, it gives the only singlet first excited state, not the triplet excited state. It is the only singlet excited state. That singlet S1 state is generated. In that S1 state is 5 to 5 star singlet state. In that singlet state, these two 5 bonds undergoing homolytic cleavage that leads to the formation of a bond between the 2 and 4 carbon, and there is a radicals are radical is, you can also represent like this. A dots can also shown like this. These are the radicals. That means 1, 2, 3, 4, 5. 1, 5 biradical intermediate. A 1, biradical intermediate. This 1, biradical intermediate, the cleavage of this sigma bond, what's happening? Like this. Here, just this is the imaginary hypothetical intermediate transition state. That will be these two radicals homolytically combined together. That leads to the formation of two radicals combined together. That leads to the formation of a double bond. And the two radicals are remaining here. Again, these two radicals are combined together. It generates the three-membered ring. It can be written like this. That is the mechanism of this reaction. This is vinyl chloropropene. Vinyl chloropropene.
Vinyl cyclopropane, sir.
Yes, vinyl cyclopropene. Right. Okay. This is the mechanism. We have the several examples are there. You can open your book and practice the mechanism for every example in the book. Right. If you have any doubt, you can ask me in the next class, or otherwise you write in a paper, white paper. If the doubt is there, just post in the Telegram group. I will give the clarification. Okay. This is about the photochemistry of conjugated double bonds. Okay. And one more example is there: intramolecular cross addition reaction. This intramolecular cross addition reaction is also appear in the 1,5 dienes. Okay, let's see. This is a small reaction. Let's see in the next class, right? So this is about the today's class. Do you have any doubts? Can you ask me? No doubts?
No doubt, sir.
Okay. Thank you.
Yes, thank you, sir. Thank you so much.